to represent the stoichiometric coefficients, A moles of A and C moles of C. Now, as this reaction proceeds, we'd like to track the progress. And we do that by defining something called the reaction quotient. The reaction quotient is the product concentrations over the reactant concentrations. And you can measure them at any time. So Q will change with time. Specifically, I take the concentration of C raised to the stoichiometric coefficient of C, and D to its stoichiometric coefficient. Same for the reactants. A concentration to the A power and B concentration to the B power. And I can calculate this value Q at any time. So if I, let's say, plot the concentrations of all the products and reactants versus time, if I start out with A, B, and not much product, so a lot of reactant, here's a lot of A reacting to form C and D, so the A concentration decreases as time progresses. B as well decreases. And let's say we didn't start out with much C and D. So they started out at low concentration and went to high concentration as the reaction proceeded. At any point I can take and plot, pick a time, and read the concentrations or measure the concentrations of A, B, C, and D and plug them in to my reaction quotient. So I can calculate this number Q at any time. I just measure or read off the concentrations and calculate a value for Q. And Q will change over time as these concentrations change. But notice, for chemical reactions, the concentrations eventually stop changing. You can see they flatlining here. There's no change with time for the concentrations. So if you wait long enough, these values of concentration stop changing, and that means Q stops changing. It becomes a constant after some time. We call that the equilibrium constant. So as chemical reaction proceeds, over time, the macroscopic concentrations stop changing, and your reaction quotient stops changing. It becomes a constant. We call that the equilibrium constant. Now, the equilibrium constant is a constant because the macroscopic concentrations aren't changing, but dynamically, the reaction is still active. That is, A and B are still changing into C and D. It's just at the same time, C and D are changing back into A and B. So macroscopically, things don't change, but the reverse and forward rates have equalized. So it's a dynamic equilibrium. Now, the interesting thing about being able to measure this K is if you do it for chemical reactions, you find the value of K is the same at a given temperature, regardless of where you start. So if you start with A and B concentrations high and let the reaction go, Q eventually becomes K. You start with C and D high, the reaction goes in reverse, and interestingly, the same value of K is achieved over time. So it's indeed a constant, and it's a characteristic of the chemical reaction. So if you measure lots of these Ks, you can kind of predict where the reaction is going to go. So you could measure Q at any time, and if you find your Q is less than your known value of K, then you say, well, wait, Q is too small, so that means the numerator here is too large. The numerator is the products. So if these products are too small, because Q is too small, I should go make more of them. So I should go towards products. So comparing Q that you measure at any time with your known constant gives you predictive power. Which way is that reaction going to go? Same thing, if you measure Q and it's bigger than K, well, that says this numerator is too large. Too many products, I should go back to reactants because I know Q's always go back to the K. If I wait long enough, reactions will proceed, so Q, the instantaneous concentrations, stops changing at this value of K. And it'll progress towards K in a relatively straightforward monatomic fashion. So here we have Q equal K at equilibrium. Now, the approach from Q to K can be monatomic as I've written it, but it actually could also oscillate. Whatever it is, it'll get to K eventually. So Q equals K at equilibrium, and what I have is comparison between Q and K will tell me which direction I have to go to get to equilibrium. I can measure this value of K. What I need to do is measure it at different temperatures because K will change with temperature. So if I do this reaction at 25 degrees C, I might get a different value of K than I would at 50 degrees C. But either way, at 25 degrees C, regardless of how much A, B, C, and D I start out with, I'll always go to that same 25 degrees C value of the equilibrium constant K. So I can track chemical reactions using the reaction quotient, knowing where it's going to end up the value of K at equilibrium.